All right, so let's continue our study of the classical groups. We're going to go back and start with our vector space. Right? These are the things that we establish in order to have a vector space. And I'm adding into that now the inner product. So it's now an inner product space. And we've discussed in our last lecture that all the possible inner products, bilinear and sesquilinear, in full generality, those seem to be the entirety of the different possible inner products. And the name of the space, the basis, the dimensionality, and the underlying field. Now, what I want to highlight in this talk is the idea of matrices and how they show up in our work in different ways and how they've been generated from different work. So from linear algebra, we know that maps from the vector space to the vector space are linear transformations. And linear transformations can be represented by a matrix. They can. And we also know that we can have a basis transformation from E mu to, say, E nu. Or no, I guess how about E hat? From the unhatted to the hatted basis. And those guys can also be represented by a matrix, a square matrix. And interestingly enough, despite all of my pleadings to the contrary in the material I covered on general relativity, the inner product can also be represented by a matrix. And all three of these matrices are square matrices. And all three of them are indistinguishable when you just look at them, right? I mean, well, they're indistinguishable in the sense that they are all square matrices whose entries inevitably come from the field F, whatever that underlying field is. So all of these matrices look the same. So I want to indicate how Gilmore handles these matrices as mathematical objects. And for the basis change matrices, he will write, let's see, I'm going to literally do it the way he does it. E hat sub j is A, J, I, E, I. So the hatted basis is related to the unhatted basis by these matrix elements, and he puts the row matrix in the lower position, the column matrix in the upper position, and the vector, the basis vector itself keeps a lower index. This is consistent with how it's usually done in the physics literature as well. But this matrix here is the basis transformation matrix A. And likewise, going backwards, right, from the hatted basis to the unhatted basis, you would use the inverse matrix. Right, sort of like this, right? You multiply by this inverse matrix. When you do matrix multiplication, it's the two adjacent indices that have to be the same. So this is simple basic matrix multiplication. It'll leave a k'th element, and ultimately this becomes, on the left-hand side, you would multiply by this guy, and you end up with that. And this, of course, by the definition of inverse, gives you the unhatted basis in terms of the hatted basis. And then, of course, the notion of your regular run-of-the-mill average vector inside the vector space. And if we have our average vector inside the vector space and we execute a change of basis into the hatted basis, we have to make sure that we would just put in this unity right in here. This part of the unity converts this to the hatted basis, and this part of the unity converts the components to the hatted basis. And from that, we derive the idea of contravariance, right? The components transform under this basis transformation contravariant to the basis vectors themselves. So that's the way Gilmore presents this. It's pretty standard stuff. The possible confusion with other linear algebra related treatments of this would be this up and down stuff. The raw math presentation doesn't always do that, and they would be happy to do this for the same thing. And the interpretation now is a matrix times a column vector, right? If this is the structure for a matrix times a column vector. So is this, by the way. That's the structure of a matrix times a column vector. So we interpret this as a, there's a column vector here with E1, E2, all in those positions, and this will give us the new basis as a linear combination of the old basis. Now, these transformations here, these basis transformations, they are the underlying transformation of the coordinate system. Whenever someone says coordinate transformation, they're actually talking about the basis transformation, and the coordinates of a point, which might be the components of a vector, those will just transform with, contravariantly in the coordinate system, but that's often also called a coordinate transformation. But ultimately, the coordinate transformation, the way we like to think of it, is driven by this formula right here. So that leaves us with this matrix and this matrix to understand. The distinction between two mathematical objects that look the same, it's a bit of an interesting subject. I mean, if you're looking at a matrix, you can't tell the difference. The way they're different is you define them differently. The red ones are the linear transformations, and the blue ones are matrices that represent the metrics. But what the real truth teller between two mathematical objects being different in this context is the following sort of general statement that pervades almost all of modern physics. Here, I will just write it down at the bottom of this screen. Objects that transform differently are different types of objects. Now, you can have two objects of the same type that are different, and if I left out this word, objects that transform differently are different objects. But what I mean is different types of objects, right? If I'm looking at a matrix and I want to know whether it's a matrix that represents a metric or if it's a matrix that represents some linear transformation inside the vector space, the distinction between those two is their definition, but ultimately these objects transform differently when you select a basis transformation. So if I choose a basis transformation, which is a very arbitrary, choosing a basis is a very arbitrary project. We need to be able to choose arbitrary bases and still preserve the qualities of these objects here. And so the way this works is this guy and this guy do not transform the same way. Let's first have a little bit of a look at what we mean by a matrix representation of a metric. So this is our definition of the matrix, the metric matrix elements. And if I chose to write that as literally a matrix, I might come up with G11, G21 to GN1, G12 to G1N, finally ending with GNN. Now, I've said many times this is not a good way to think of the metric. And that is because we were previously working with the idea of a metric as being a 0-2 rank tensor. Right, a 0-2 rank tensor, very much like this. In the coordinate representation, we talked about it like that. And it is not generally a good idea if you're going to be thinking of these kind of objects to immediately throw it down in a matrix, unless you're just trying to list the different matrix elements so people can see what they are, right? So it's not uncommon to do this in general relativity and in physics. It's just not operationally such a good idea. But it's not, there's no real core sin as long as you know what you're doing, right? So now we're in a new sort of intellectual world where we kind of have to look at the metric as a matrix. So the rule is now going to be we're going to have to come up with a rule that allows us to take two vectors, multiply, use this matrix somehow, and produce a real number. And that's a bit of a challenge, right? Because if you have a matrix and a row vector, well, that gives you a row vector. But if you're going to treat, these are two vectors from the same vector space. So if you treat one as a row vector, you've got to treat the other as a row vector there, right? The other's a row vector too. Or the other should be a row vector. And now you have a row vector from this multiplication, and now you have another row vector. And how do you take two row vectors and get a number, right? How do you do that? Well, you can't just straight up do it using pure matrix multiplication. Obviously, you have to assert that you're going to take one of those row vectors and transpose it and turn it into a column vector. So in the end, this ends up being a number, right? So this will be a matrix times a column vector, and then one of these is a row vector. Now you have a row vector times this guy here is a column vector, and a row vector times a column vector will in fact be a single number. So that's the rule when you use this kind of matrix if you're going to try to evaluate the inner product of two vectors. Now the specific way that our book does it, Gilmore does it, is he'll take, and I'll use literally his notation here, he'll take two vectors u and v and say, okay, there's the inner product. We're going to write these guys out, v, j, e, j, u, whoops, I used vi, sorry. I want to do it exactly like he does it, vi, ei, u, j, e, j, right? That's just substituting, these are abstract vectors here. Now I'm substituting the those little vector arrows on top to separate the vector part from the, they're messy, I don't like them. So now we make the obvious substitution. We basically cast these abstract vectors into a coordinate basis this way. We use our rule for a sesquilinear form. So we end up with u, j, e, I, that's an I, e, j, and then this is vi conjugate, right? That's the sesquilinear form extraction. This guy here is a complex number. This guy's a complex number. That guy's a complex number. We're assuming complex numbers, obviously. And then we make our substitution using sort of this prescription, and we get u, j, g, I, j, v, bar, I. And now when you interpret this as a matrix, what you see is that we're automatically treating this as a row vector of components and this as a column vector of components, right? Remember, in the basis transformation, everything kind of looked like a column vector. All these e's were column vectors, and for what it's worth, the components were row vectors, right? Because it's being summed over the inner indices. If you want to think of it in that fashion, if you want to think of basis transformation as matrices, which we kind of do. Because our classical groups are, by the way, groups of matrices that transform bases, right? That's the whole point. But here, now we have the definition of the inner product of two vectors automatically induces what amounts to a transpose on V, because you're treating V like a row vector. And you have these two down indices. So in order to, but regardless of the down indices, these you're summing over the inner, on the inside index for the V, which indicates V is basically being treated like a row vector, where uj would be treated like a column vector. So that's the nature of the matrix, of how the matrix for the metric has to be. If you're going to think of it in terms of a matrix, that's how you have to think of it. I guess in the most abstract way, we could write something like G of vector V, vector U goes to, it goes to V transpose G U, right? That's how you that's how you calculate that. All right, so once we understand this, the next really super important question is, how does G behave under a basis change, right? That's always the important question. The basis change kind of drives everything. And the reason it drives everything, you might wonder, okay, why is this damn basis change so important? The basis change of vector spaces is essentially establishing the coordinate system. When you choose a basis for a vector space, you're essentially establishing the coordinate system of the vector space. And in physics, we have this principle that any coordinate system, the physics is unchanged. So understanding how when we randomly, arbitrarily change the coordinate system, how other mathematical objects behave under those transformations is critical, because we have to make sure that the entire theory as a whole stays exactly the same, or presents the exact same conclusions in any coordinate system. Otherwise, our arbitrary mapping of these mathematical objects give us different physics, and we can't have that. We assume that that's not the case. That's a fundamental presumption of physics. It's an essential core assumption of special relativity, general relativity, and therefore it pervades itself. It oozes into every other element of physics. So these coordinate changes are really important. So we already studied in an earlier lecture how G changes under how this changes under a coordinate change, and it's pretty straightforward, right? We're going to use this basic formula here. We start with the basic definition of the metric in the hatted system, right? That's pretty straightforward, and we write the hatted basis in terms of the unhatted basis, and here's where the matrix comes in. Notice that this is the straight up transformation matrix of the basis system. So that comes in. Now the obvious next step is we're going to pull this out here with its conjugate. We're going to assume a sesquilinear form. Pull that out here with its conjugate. Wait a minute. Sorry, these i's over here should be j's. J, like that. And then this becomes AL, J, EI, EJ, AKI conjugate. And that leaves us with the fundamental formula for the basis transformation of the metric element. Now, the time we did this before, I actually went to show what was required so that these elements would remain the same. I gave sort of I guess that was a bit of foreshadowing. Well, I got ahead of myself, right? We should have talked about some of these ideas first. But the point is given an unhatted basis, I take the fundamental transformation matrix, and I essentially take the conjugate, and look, this conjugate, you see how it's being multiplied by the inside, right? And this one is being multiplied by the outside. So essentially, the way this actually looks is we end up having the transpose, right? This is the transpose, and so this is the conjugate transpose over here, and this is the regular matrix over here. So if I were to write this in matrix form, I would get the matrix A times the matrix G times the matrix A transpose conjugate, like that. And now, by the way, you see exactly where these conjugate transpose things start to come from, right? It's to do with the sesquilinear nature of the sesquilinear form. So if you see a metric that's being used in the form of a matrix, you have to understand that its transformation property under a basis transformation, the basis transformation always looks like this. It's this linear combination. The new basis is a linear combination of the old basis. Or the basis you're transferring into is a linear combination of the basis you're leaving. And this is the transformation rule that you have to live with. Really, this one here. We don't actually write it this way very often. I'm just sort of doing that to describe it as a matrix form. But this is the formula we use. Now, if this was a linear transformation, right, if this was this guy, if this was just a regular linear transformation inside the vector space, well, that transforms totally differently. That does not use this rule at all. It's a matrix, but its basis transformation is completely different. The basis transformation of the linear transformation in the hatted basis, right, is going to equal. Let's see if we could do this. So this one we'll do a little bit less formally, right? So we have the hatted basis. We have the hatted basis. Oops. The hatted basis and the unhatted basis. So presume that we know a linear transformations matrix in the unhatted basis. We'll call that matrix B. We want to learn what is that matrix in the hatted basis. Well, we know that the basis transformation will give by a matrix A. So we're going to say E hat is AE, right? And the components, right? The components of a vector, we're going to use the other. We're going to use the inverse, right? So we're going to say V hat equals A inverse V, right? So where the V really is the components of the vector. It's just contravariance and covariance. But notice also what we have is we have E equals A inverse E hat, and V equals A V hat, right? Where now we're running the whole logic backwards, where this is the starting basis, this is the transformatric matrix that gets us to the new basis, but we're going the other way. So everything's just named differently. So with these facts in mind, we presume that we know B, and we want to find out, well, how would we use B to operate on a vector that's in the hatted basis? Well, the first thing you do is you move the vector from the hatted basis to the unhatted basis. So I would take my hatted vector and operate by A, and this guy, right, is, as we see here, is in the unhatted basis. So with that, I just operate with B, because B is allowed to work in the unhatted basis. And then the result is BAV hat, and that result is in the unhatted basis. And then I just, it's the components in the unhatted basis, so I just move them to the hatted basis this way. And now I look at that and I say A inverse BA, well, that is going to be the hatted version of B. And it operates on V hat. So B hat, the transformation is a similarity transformation with the matrix A driving the similarity transformation. Now sometimes this ends up in some work the other way around. It's A, B, A inverse. And that all has to do with the way you define the ultimate matrix transformation. If you decide that you want the components to transform with the normal matrix, not the inverse, then you get it to go the other way. In many linear algebra books, that's how it's done. In fact, it's how it's done. But not the convention in Gilmore. It would be this in Gilmore. But then the other important point, of course, is that this similarity transformation is not the same as this. Conjugate transpose, to change the metric, it's a different transformation. So it's the same, it could be the same A, right? The ultimate basis transformation, I don't think I put it in here anywhere. It could be the same A. Let me erase this, hold on. But it could be this, when I say the same A, what I mean is it could be the same basis transformation. But the way that basis transformation affects the metric is using a totally different formula. It's using this formula, which involves conjugate transpose. There's no conjugate transpose here, right? But if I write B hat equals B inverse, equals A inverse BA, there's no conjugate transpose there. That's a totally different process.